Hello, and welcome to this TechPipe video. My name is Pablo Salazar, and I'm currently working in CMG as a reservoir simulation engineer. Today, I'm going to talk about the use of formulas in results. The objective of this short video is to provide a quick guide on how to use formulas in results to create additional output parameters that can help you in your post-processing activities and enhance your post-processing experience. I will be talking about post-processing simulation results, the type of formulas that you can create in results for your simulation post-processing. And at the end, I will show a short demo video on how to implement these formulas using the results interface. The application results is the CMG solution for simulation post-processing. As you might be aware, you can access results via the CMG launcher in exactly the same way as you can access all the other CMG tools available. In general, using results, you can carry out graphical analysis of CMG reservoir simulation outputs, compare simulation outputs with field history and well log data, and assemble dashboard views showing different plots of interest. The interface is user-friendly and well-organized and is designed to make these functions quick and intuitive. In general, to use results, you will need either a simulator SR3 output file, a field history file, or well log files. If you want to compare simulator output with actual field history and well log data, you will need the SR3 file and the associated field history and well log files. You can also apply templates for your results project for a fast and easy definition of commonly used set of plots. For this, you will need to import the appropriate templates for this purpose. Why post-processing simulation results? Post-processing simulation results can help you in different activities. Post-processing in reservoir simulation ensures that results are physically consistent and aligned with historical production and pressure data. It enables engineers to evaluate reservoir performance through key indicators such as recovery factor, production rates, and pressure behavior over time. By analyzing processed outputs, optimal well placement, production strategies, and enhanced recovery opportunities can be identified. Post processing also supports decision making by providing insights for economic evaluation, uncertainty quantification, and risk assessment. Through visual representations like maps, cross sections, and 3D models, complex reservoir behavior becomes easier to interpret and communicate. Additionally, comparing different simulation scenarios allows for data driven selection of the most effective development strategies, while identifying model deficiencies helps refine input data and numerical parameters. Overall, post processing transforms simulation results into clear, actionable information that supports technical collaboration and informed decision making. In a nutshell, post-processing of reservoir simulation output is a vital step that transforms raw numerical data into meaningful insights. It allows engineers to validate model accuracy, visualize reservoir behavior, and evaluate different development strategies with confidence. Through careful interpretation, post-processing bridges the gap between complex simulation results and practical decision making, supporting both technical assessment and economical evaluations. Beyond analysis, effective post processing enhances communication, turning complex outputs into clear visuals and summaries that guide collaboration across disciplines. In essence, it is the stage where the simulation results gain purpose and value, converting data into understanding and understanding into action. Formulas in results. In results, through the input formulas node, you can create formula-based time series using data from any of the available data sources, such as SR3 files and field history files. And you can create formula-based spatial properties. In general, formulas are entered using a Python code, which is an easy to use high level programming language. When a formula-based time series is created, it will behave the same way as any other time series. Formulas can be used to define other formulas, like having formulas within formulas. And results will always validate formulas to ensure there are no circular dependencies. In a similar way, spatial properties can also be created, and they can be displayed as any other spatial property in your model. The formulas page for time series and spatial properties are organized in a similar way, although some additional settings and options are available, in particular for spatial properties. Let's see how we use these functionalities with a very short demonstration. As I mentioned before, to use results, you need an SR3 file, which is one of the main outputs from any simulation with any of the simulators. So here I have my SR3 file, and I'm going to drag and drop my SR3 files into results to open the results interface. Once I open my results interface, this is how it looks like. So on the left-hand side, you have your tree with different options in results. As you can see, I have already a set of plots automatically created by results because I'm using two templates that allows me to speed up the process of creating standard plots. In the tree view, you can access the formulas node that I mentioned before. So let's start talking about time series formulas. So if I go to time series, so this is my time series interface. So the formulas page is organized into several distinct areas. The first step in creating a formula is to insert a formula in the formulas table, which is this table here. So I'm going to create my first formula. So the first step is to give a formula a name. I'm going to call my first formula as half production oil rate. So let's imagine I want to create a formula that allows me to calculate half of the production rate for all the wells, which is not a standard output in the SR3 file. So in order to do that, I created my formula, and now in the independent variables table, which is this table here, I need to select the independent variables that I'm going to use to do this calculation. And in this section, you have different columns. Okay, so in the status column, as you define a formula, I'm going to show you now. If you have any problems with your formula, you will see in this column a red box with a cross showing that in your formula there are some errors. Okay, because results automatically validates the formula. In the primary column is where you select the independent variable that you want to use as the primary independent variable. A little bit later, I'm going to show you that this is important because in some cases where you have formulas with multiple independent variables, is here where you can tell results which of those variables will be the primary value for repeated plots. Okay, I'm going to explain that a little bit later with an example. In the name is when you select a variable, automatically results will give a name by default to that particular variable, but you can also change that name manually. In the origin type is where you select the type of data are you going to use. So here you can select data from wells, from groups, from regions. You can select data at field level. This is the column where you select that. In data source is basically where you select the SR3 file that you want to use to read that variable from. Means that if in your results project you have more than one SR3 file uploaded, you can use variables for multiple SR3 files in the same formula as well, so you can combine. In the in the UVA, or yes, in the origin name is where you select the data origin that you want to use as an independent variable. In UVA, so for example, if you are creating a formula to calculate a variable for a specific grid block, this is where you define the UVA of that grid block. And then in the parameter is where you select the actual variable, the independent variable that you are going to use. And in components, you can select also a specific parameters for a specific component. So for example, in compositional simulations from GEM, you can use a specific parameters for specific components as part of the calculations in a formula. Okay, so let's do an example. So I have defined now my formula to calculate half of the production oil rate. So I need to insert at least one independent variable. So as I said, results will give a name by default. Here you can select if you are going to use data at well level, at layers level, group, sectors, special history, or block properties. I'm going to select wells, and then I'm going to select in this case, I have only one SR3 file uploaded into my results project. So I'm going to select that SR3 file, and I'm going to select my first well. And the parameter that I'm going to use is my oil rate, oil production rate at standard conditions. Okay, and then as you can see, there are a few additional settings available here in this section here. So in, for example, in formula start time and end time, you can define the range of data to be used in the selected formula. So for example, you might not be interested in this calculation to happen for the entire simulation period, but for a very specific time period. So you can untick the default, and then you can select the time range on which you want this calculation to happen. Okay, and I'm going to talk about this option in the next example. And then in this box is where we use a very simple Python code to do this calculation. So in my case, because I want to calculate half of the production oil rate, I'm going to say that my formula is TS0, which is this variable, divided by 2. And that's it. And now I get a message here in the validation box saying that my formula is valid. So everything is fine. So now if I go back to my time series, and then I look for wells, and I select my first well, now I can search for that variable that I had just created. And here it is, half production oil rate. So I can add this to a new plot. And this is half of the production rate of this well. To validate that, I can add into the same plot the original oil production rate for that well. And that's it, but they are in different axes. But if I do normalize this to, let's say, 650 and 650 here, I can see that the original time series coming from the simulation output is the orange line, and my formula or my variable, which is half of that production, is coming from that formula. So this is a demonstration how you can use a time series formula with only one independent variable. In addition to that, I can also show you that automatically results has applied the same formula to all the wells in the model. So the same calculation is being done for all the wells automatically. Now, if I go back to my time series formulas interface, I'm going to insert another formula that I'm going to call fractional contribution. Okay. And in this formula, I'm going to use two independent variables. All right. So I'm going to select first for wells, I'm going to use the oil rate again. And I'm going to insert another independent variable, but in this case, it's going to be groups from groups. And I'm going to select the production group, okay, which is basically a group where all my producers are belong to. And I'm also going to select the oil rate for that group. And then I'm going to say that this formula will be TS0, which is the rate for each well, divided by the rate for the group. So in that way, I'm going to calculate the fractional contribution of each well into that group to the total production. And this is where sometimes this option substitute for only the primary independent variable when repeating. Means that because results will repeat this calculation for all the wells, I need to tell results that every time he's repeating the calculation for each well, this second independent variable here will be the same for all the wells. So results will only change this variable for the multiple calculations. And at the same time, I can use this example to set a specific time frame for which I want this calculation to happen. So I want results to apply this formula only for the period between, from 2010 to 2020, not for the entire simulation period. And that's it. So if I now go back to my time series, and I select a plot for a well, and then I look for that fraction contribution, which is here, and I add this to a new plot. So now I can see that for this particular well, this is the fractional contribution of the total production coming from this well. So if I do add, for example, multiple wells to this plot, okay, so, and then I'm going to customize this a little bit because they all come in the same color. There you go. So now I can see the fractional contribution for each of these individual wells to the total group production using a time series formula. Moving on now into the spatial property formula interface. You can also define formulas for any spatial properties in a similar way. This interface is organized in exactly the same way as for time series. So if I want to create a formula now, for example, to calculate KH, I'm going to call my formula KH. And then I need to define two independent variables. So I'm going to use this SR3 file. And then the first property that I'm going to use is the thickness. Okay. And then you can either use the option to synchronize the calculation for every time, or you can select a specific time step. And then my second independent variable will be the horizontal permeability. And in a similar way, I can define my formula as SP0 times SP1. So in that way, I will be able to calculate the KH for every single grid block in my simulation model. In the spatial properties interface, you also have a few additional settings that are available when you define your spatial property. So for example, you can you have this option, substitute undefined value if mathematical error occurs in formula. So so you can but it's automatic, this box is automatically ticked. You can untick this option if you want to use a specific value when for a specific formula a mathematical error happens. So for example, if you are using a variable, an independent variable that in some grid blocks for some reason is 0, like thickness, for example, and you are defining a formula where the thickness is going to be used in a division, for example. So mathematically it's not possible. You can define the value that the results use for those cases. On the on the other side, you can also specify the time tolerance. For example, when you are using two different data sources. As you know, two different simulation runs might not have necessarily exactly the same time steps. So you can use some time tolerance to be able to do the calculations combining two different data sources into one formula. On the other side here, you have this option here, which allows you to assign this property that you are calculating either to the matrix or to the fractures. So this option will appear inactive unless you are working on a dual porosity or dual permeability model. Okay, so by default, all models use matrix grids. And this, so therefore, any spatial property that you are calculating will be allocated to the matrix grid. In the case of a dual porosity, the model will have both matrix and fractures. So, so you can select to which of those this property will be allocated to. You also have these neighboring function options here. These are functions that operate on spatial properties such as oil saturation, pressure, to produce new properties that can be an average, a sum, a minimum, a maximum. None is also an option. When the average option is selected, you have few additional options here, so you can select the type of average that is going to be calculated for that specific property. With the stride mode checkbox, you can set the stride range to be used for that calculation. The IJK average values can be viewed on 3D views. When you are in stride mode, the property values of all the grid blocks within that requested range are the same. So this is kind of equivalent to a property upscale without grid upscaling. If the stride mode is used to calculate the property value, the resulting reservoir will typically look like a cursor, as several blocks in this particular range will have exactly the same value. So going back to my formula, so I have defined a formula here to calculate the KH for all the grid blocks in my model with this formula. So now if I go to my 3D view, as you can see in here, I will have that as an additional spatial property that is available for me to display. And here it is, my KH. So now I can display in a 3D view the KH, which is the multiplication of the thickness times the horizontal permeability for all the grid blocks in my simulation model. And that brings us to the end of this video. I hope you found the information helpful and that it gives you a boost in your simulation post-processing work. If you have any feedback, questions, or need technical support, feel free to reach out to us anytime at support@cmgl.ca. Have a good day.